Hello, can the Zoom people hear me? Thanks for. We lost the first few parts, but it's probably okay. Right. Yeah, I stopped it. I stopped it before the start of the class. Yeah. Okay, now everything should be fine. Here, all the xi's are id, and the Sn is only a function of the first n inter-arrival times. Okay, so now we are talking about the n plus first here. So these guys here are independent of this guy, so I can drop it. Okay, so this is because of the fact that we are dealing with renewal processes. So all the inter-arrival times are independent. So the last step is not so difficult. By memorylessness of the xn random variable, this is equal to probability that xn plus 1 is bigger than z. Because this part is common. Maybe I can use this. This part here is the common part, can throw away. Okay, this is by memorylessness. And then what happens here is that I know that the complementary CDF is given by, the complementary CDF of the exponential is given by this. Okay, so this last step here is by memorylessness. Memorylessness of the xn plus 1 random variable. Okay, so any questions on this sequence of steps? People at home, any questions on this sequence of steps? This is all in the book, but I think the book goes a bit fast here.
Can you repeat again why the Sn equals to tau is being removed?
Okay, good. Because Sn depends on the first n random variables. Because depends on the first n inter-arrivals. Sn is equal to x1 plus x2 up to xn. Now, all these guys here, xn plus 1 is independent of x1 up to xn. This random variable is independent of xn plus 1 because this random variable x is only a function of the first n random variables. Okay, so what we are utilizing is this fact here. What we are utilizing is this fact here. The probability that x given y is equal to the probability of x if x and y are independent. All right, something like that. Okay, essentially what we are using is this. Although what's happening here is a little bit more complicated because here we have a random variable and another random variable and another one. But this guy here is only dependent on the first n. This is the n plus first. And everything is independent. So the first n are independent of the n plus first. Okay. So just to add on to this explanation here, we have that xn plus 1 is independent of x1 up to xn. Okay. Right. So hopefully that answers your question. Right. Okay. So now what have we shown? What have we shown? So after all this calculation, we have shown that following. Just to copy this, we have shown that this is equal to e to the minus lambda z. Okay. However, coming back to Joseph's point, all right, we are not done yet, but what we are going to invoke is yet another independence property. Okay. Consider, all right, probability of z greater than z condition on nt equals to n, s1 equals to tau 1, all the way up to sn equals to tau n. Now, I just want to remind people that this is exactly x1, and this is x1 plus dot 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 plus xn. Okay? So we can insert all these things without any loss because we can drop all these. They are independent of this. Okay? So we can insert all these without any loss, and we still get e to the minus lambda z. Okay, you can run through the previous calculation. Notice what I have done is I have kept this guy around, and I just renamed this to be tau n. Nothing. You can rename it to whatever. But even if I inserted the first n minus 1 arrival epochs, this is not going to change my calculation. Because the only important calculation, the only important fact is that this guy here is at tau. All right, doesn't matter where this guy is. That's what I'm saying here. Okay, so actually, okay, so now what happens here is that, but what we are conditioning on as n equals to tau n, this describes the entire evolution of the process up to and including time t. I.e., okay, if I know this entire collection of random variables takes on a certain value, I know how this whole guy evolves. Nt from tau up to and including t. That means that if I know this entire realization of all these random variables, then I also know this guy clearly, right? Because I would know exactly when the arrivals arrive and the fact that at time t, which is bigger than tau n, nothing happened between tau n and t. Okay, so I know the entire counting process up to and including time t. So these two shaded parts are exactly equivalent in terms of the realization, of this random process. Okay, so what I'm saying here is that I can equivalently rewrite this guy up here as z greater than z, conditioned on the entire process up to and including time t, equals to e minus lambda z. Okay, so this is what we have actually shown. Okay, this means that by integrating or averaging, notice that this is a random process or random variable. Now we can average over this random variable or random process, aging over n tau less than t. We get that. We get the marginal result. Z bigger than z is e to the minus lambda z. And this implies that because now you have these two relationships, this relationship and this relationship. Okay, so what it's saying is something like, okay, probability of z given whatever is the same as probability of z. So z must be independent of this whatever. Okay, because if say I have an x here and this relation holds, z is independent of x. Except that now my x is a bit more complicated as this entire Poisson process. But nevertheless, what we can say is that z here is independent of n tau less than equal to t, which completes the proof. Which completes both proofs actually. This is part 1 and this part 2. Okay, so what we have done, let me go through this whole proof again. Okay. First, we look at the picture. Oh, Teo Jing Yang said equality part doesn't seem obvious. Okay. Let's see. Let's go through the proof. So the statement is that z is exponential lambda, and furthermore we have all these independence relationships. We only need to prove this one. Look at the picture. All right, in the picture, nt is equal to n, which is equal to 2. Okay, so now we have this picture, and we are going to compute something like this. All right, so this sequence of steps is important because it illustrates the properties of the Poisson process. What properties are we using? We are using the fact that these xi's are ID, and in particular, the xn plus 1 is independent of Sn because this guy here depends only on the first n, and this is the next interarrival. Okay, so what have we shown up to here? If you follow all the steps, but you should. Okay, so we have shown this. Okay, but the fact is that this conditioning, I can basically stick in S1 up to Sn minus 1. It does not affect the argument. All right, this requires a moment of thought that I'm not going to belabor. But if I know this entire process here, if I know this entire realization of these random variables, nt equals to n, and S1 is equal to tau 1, Sn equals to tau n, then we can sketch out the entire evolution of the Poisson process. In particular, if you are not convinced, this is my S1, this is my S2, and this is my Sn, or this is my Nt, this is my T. All right, if I know this, let's say only S1 and S2, okay? Then I will know that I have an arrival at tau 1 and I have an arrival at tau 2, and there is nothing happening here. So I can draw out this entire curve. Oh my. I can draw this entire curve from here up to this point. So what I have done is I have described this entire process up to and including time t. Up to and including time t. That's what this is saying here. And so I do not know whether you're convinced or not, but I am convinced that this describes the entire process up to and including time t, i.e. this yellow part. I just drew a picture for you. Okay, so what we have shown is this. But this is a certain random variable. You can call it, don't call it x, but call it n. You can average over it, take expectation over it if you wish. All right, and then you get this. But these two statements together say that this part here is independent of this part here, because the right hand side is the same. All right. So what we have shown is that this, and then the marginal is of course this. So part 1, part 2. Okay. Any questions?
What exactly are you averaging for the?
Okay.
Like,
Maybe very fast.
You write the event n tau for 0.
It's not event, it's a random process. Okay. So thank you, but it's not an event. All right. So let us explain this part. This averaging may be a bit fast, but then let's see what happens here. How to get from here to here, right? Okay, so let's see.
Even the statement, right? Like, what does the statement say? It says probability of z greater than z. Condition on.
We should actually put almost surely here, because this is a random variable. What we are conditioned on is a random variable. Okay. Actually, to be absolutely pedantic, right? This is actually going to be equal to some nt for t tau less than t. Little n tau, where tau is less than t. To be absolutely pedantic. Because this guy here describes the entire process up to and including time t. Okay, i.e. this actually takes on value n tau less than equal to t. But this is true for every realization. So I might as well put the random variable inside here. So this is a random variable. So what I'm doing, let me explain, is probability z bigger than z condition on random variable n. This random variable n here describes the entire process up to and including time t. Okay, so this is actually, this what I've written here in red is actually a random variable. Okay, now, what am I talking about when I average? Okay, so what I'm doing is I'm doing maybe, okay, this is a long-winded way of saying some density and the n. Okay, this is nothing but probability z given z. This is the meaning of what? This is my meaning of averaging. Okay, or taking expectation. Because here, this guy here, this is a random process. You can set it to be a particular instance of that random process. You can still take expectation like this, and you will get this marginal. Okay? So this one is too fast in the book. I'm going to cut this away, okay? Too fast in the book. That's why I do it slowly here for you. Thanks for asking. These are good questions. Where am I now? Okay, I'm here. So this completes the proof of part 1, part 2. This completes the proof of part 1 and part 2. People at home, any questions? Or this is not, this is you were at home just now.
I was talking here.
People at home, any questions? Okay, I think I should pause for a moment. All right, so now we are going to talk about two important things. All right, that is the stationary increment property and the independent increment property. It will follow in a very straightforward way if you understand this proof. That's why it's important to understand this proof. Okay, there are two important things. Stationary increment property. So I don't have to write this every time I call it the SIP. Now let's look at this. And this is the number line. We start with 0, and we have Sn here, Sn plus 1, and Sn plus 2 here. Okay? And what happens here is that we arrive at the time t. This is just a picture above, except that I didn't draw the counting process. Okay? And we could have many arrivals here that I really don't care about. So S1, Sn minus 1. Okay? So this is the important part, the red part I'm going to talk about. Okay? So you remember I called this Z1. All right, and we did a lot of work on this Z1. We did a lot of proof on this Z1. We showed that it's an exponential random variable, and it is independent. What is it independent of? It is independent of this entire path. This yellow thing that was also highlighted in yellow just now. Right? The Z1 is independent of this yellow thing. And what is the yellow thing meaning? What do we mean by the yellow thing? It is the entire process up to and including time t. Like this. Right? That's the yellow thing. Okay. So now let us define a new random sequence of random variables, which is Z1, Z2, Z3 that starts from here. Okay. Now, okay, so define properly. Let's define Zm to be the time from the m minus first arrival after t to the nth arrival. Okay, so let us plug in m equals to 1. Then we are looking at the z from the 0th arrival to the first arrival. So z1 is exactly this guy here. Maybe I should use this pointer, this one. Z1 is exactly this guy here. If you plug in m equals to 1. If you plug in m equals to 2, what is it? The time from the first arrival after t to the second arrival after t. So this guy is Z2. Understand? You plug in m equals to 2 here to this definition. Got it? Yeah, so the point is that fact xm plus m is equal to zm. For m is bigger than, can I put 1? Can m be 1? In wrong. Can m get M1? Very good. Super. In wrong is understanding this. M must be bigger than 2 because I mean xn plus 1 is this guy, right? So not allowed. This is xn plus 1 here. So cannot, right? Okay. So this is true. Okay. So what do I want to talk about? I want to talk about the stationary increment property. I'm not defined it, but what we have shown is that condition on nt equals to n and Sn equals to tau. This was part of the proof. Z1 up to Zn continuing on are IID. All right, and they are IID exponential lambda random variables. Why? Because this one we proved very difficult that this is exponential lambda. Z1 is exponential lambda. I talked about it just now. But Z2, right? Z2, as Ingrong said, is xn plus 2. Xn plus 2 is an exponential random variable with rate lambda. So is xn plus 3 equals to Z3. Right? So all these guys are IID random variables. And they all have the same distribution. Now they are, in particular, they are independent. Why? Because this part here is independent of this part here. And Z1 is only part of this part here. Right? So now by conditioning, as what we did just now, and I explained in great detail to Jing Yang, okay? By conditioning on S1 to Sn, we can put tau 1 here, we can put tau n here, but we're not going to be so amateurish here. So let's remove all this. By conditioning on all these, as was done above, and I explained and how to average, we see that Zi, let me write it like this, I running from the infinity, are unconditionally IID. So they are IID on their own, without conditioning on anything. They are unconditionally IID. So what does this mean? We created a new process. That's the Z process, okay? This new process here, that is a sequence of IID exponential lambda random variables. What does this remind you of? What does this remind you of? This reminds you of the original Poisson process, which can be described by a sequence of IID random variables, which is exponential lambda. What we call the xi's, right? But now we created from this diagram here, we just came into the room and then we watched the football match. And then this created a new sequence of random variables that we can call the Z random variables. And this has the same distribution as the X random variables that started here, right? So after I explain this, you can be convinced that the Poisson process, or the process actually, we should say process, not Poisson process, because we haven't proved it, starting at any deterministic time t is a probabilistic replica. Now, probabilistic replica has not been defined of the process starting at 0. So probabilistic replica has not been defined, but here's the definition. That means that if I look at moving from basically, if I look at the number of arrivals from t to a t prime, okay, t prime bigger than t, bigger than 0. If I look at these three numbers, 0, t, and t prime, and I look at what happened in the interval from this 0 to t prime, I look at what happened in this interval. That's what's happening here. Okay, from t to t prime. That has the same distribution as what happened from 0 to t minus t prime. Okay, so what's happening? What happened here? Maybe I'm going to draw a better picture. Okay, 0, t prime. Okay, so this random variable here describes the activity here. Right, it describes all the activity here. Now, then this random variable here describes the activity here, where this is t prime minus t. So what happened in the blue, there's no blue, colorblind. What happened in the yellow part has the same distribution as what happened in the green part. Okay? So by this notation, I mean that we have the same distribution. Okay? So these are two random variables. They are nothing but random variables. Once I fix the t and t prime, they are nothing but random variables and they have the same distribution. Okay? So definition of SIP, stationary increment property. A counting process n t bigger than 0. So this is a counting process, has the stationary increment property if exactly the thing on top holds, and t prime minus nt has the same distribution as nt minus t for all 0 less than equal to t less than dt prime. This one can be greater than 0. And what does it mean for this? If you're not familiar with this distribution thing, this means that okay, x has the same distribution as y if and only if probability x less than z equals to probability y less than z for all z. So it has the same distribution. Okay, so what have we proved? Okay, the Poisson counting process that we have so described has the SIP. We have proved above. Okay, let me repeat this argument. Okay, let's look at this picture again. And what we have done here is actually prove that the distributions are the same. But which distributions? Which distributions? Okay, look at the picture. Look at the picture. Now, we have some arrivals here, arrival epochs here. Now, we suddenly came into the room at time t, at the deterministic time. What we proved just now was that this time is exponential lambda. This time is exponential lambda, z1 exponential lambda from the above theorem. we give this a name, Z2, Z3, and so on and so forth. Okay? And we give this a name. Okay? Zm is actually xn plus m from m bigger than or equal to 2. I realized that in my previous notes, they are incorrect. Okay, so this is correct. So m bigger than or equal to 2. Okay? But for the case Z1, right? Z1 is basically the time from t to Sn plus 1. Okay? So it's not, this Z1 is not Xn plus 1. Very important. It is short, it's smaller than Xn plus 1, but it has the same distribution as Xn plus 1. Okay? Now, by the above proof, okay, we have the condition on all these objects here. All these things are IID. Okay? And they are exponential lambda. In particular, Z1 is exponential lambda. The rest are exponential lambda because we are hinging ourselves on a Poisson counting process, on a Poisson process in which the interarrival times are exponential. Okay? So by conditioning on this, as was done above, we see that the ZIs are unconditionally IID. Hence, the Poisson counting process starting at time t is a probabilistic replica of the process starting at 0. Why? If you come back to this picture, whatever happened here looks like whatever happened here. Because whatever happened here is basically a bunch of inter-arrival times that are IID, exponential lambda, which is exactly the same description as if we started at 0. These people look a bit confused. Understand? Very clear, right? Okay, but people still look a bit confused. This is very deep actually, okay? And hence, if we make the right definition, that a counting process has the SIP, if this is true, then we showed that the Poisson counting process has the SIP. We have already proved this, there's no need to prove this. I want to see whether there are any people left in the waiting room. Okay, maybe not. Any questions? Any questions from the Zoom people? How to transition from Z to N? Okay, I think I understand. Zheng Tian. All right, so when we look at this process here, okay, when we look at this process here, we have this bunch of random variables Z. What we can then create now is a new counting process that starts here. We can create a new counting process that starts here onwards, and we can call that counting process N of T prime minus T, where T prime is bigger than T. So that is a new counting process that is indexed by T prime. Okay, so that is a new counting process. All right, sorry, this should be NT prime minus NT. This restarts the whole counting process, restarts. So it's as if you go into the room, even though there were 2 goals already scored, you didn't see them. So whatever goals that you're going to see in the future are new goals. All right, so now from this Z process, Zheng Tian, we get this new N process. Okay, we can create. So it's a new start. Yes, it's a new start. Yeah, thank you. It's a new start. No more, we go back to 0 goals because we just came to the room. We didn't see the goals, even though there were already N goals. Okay, so it's a new start. We created this new counting process. Yes. Oh, thank you, Zheng Tian. Okay. All right, so we proved the SIP. So, all right, so notation. We define N tilde for the sake of notation, for the sake of simplicity, to be N of T prime minus N of T. Here, it only makes sense to talk about T prime larger than T. Okay, this denotes the number of arrivals in the interval T to T prime, this inclusive. So Zheng Tian and everybody at home, if you are confused, you can think of this T here as 0. Then this is exactly a new counting process that I start at T. This is 0. If T is equal to 0, then I create a new counting process, right? In which I restart 0, and then this whole new process that I see from the time T is a probabilistic replica of everything that I've seen before. Okay? This is just notation. There's nothing to talk about. All right? definition. A counting process. Now I'm going to talk about IIP. NT, t bigger than 0, has the independent increments property, which we will denote by, we abbreviate by IIP, if for all k and for all 0 less than t1 less than t2 less than ... tk, the random variables n of t1, n of t1 to t2, n of t2 to t3, and n of tk minus 1 to tk are independent. And remember what is meant by a k random variables being independent. It means they are joint distribution factorizers. So pictorially, what's happening is as follows. Okay, so this is tk, this is 0. No matter how I choose the times in between, okay, the number of arrivals here, and the number of arrivals here, and the number of arrivals here, and here, and there, so colorful, right, are independent. No matter how I split my time, they are all independent. Okay? So that is the definition. But what we want to prove is that the Poisson process has this property. Okay, here. The Poisson process has the independent increments property. Okay, right? So what we can do is, again, we spend a lot of effort and time and energy to prove the theorem that we proved. So why not we use it? It's almost automatic if we understand the implication of part 1 and part 2 of the memoryless theorem that we have proved. Let's call it the memoryless theorem, because it all comes from the memoryless property. Okay, so proof. Okay, so we have this picture here. I like to draw pictures. 0 as n plus 1 as n plus 2. Okay, and we somehow come in at the arbitrary deterministic time. And we define this to be z1, this to be z2, and this to be z3, and so on and so forth. Okay, but we already proved in our memoryless theorem that z1 is in the z1 is the same as z, is independent of this family of random variables. Okay, we have to be precise and get rid of this. Okay, so this is basically what we proved just now. So I'm just utilizing it. So in terms of picture, what is this? What's the meaning? It means that this part here, which is this random variable, is independent of this part here, which is all the activity that happened up to and including time t. All the activity here. Understand? All right, you see the picture, right? Now, this implies that if I give these names t1 up to tk minus 1, okay, then I can basically talk about the activity from 0 to t1, okay, as my n of t1. That's all the activity. That is all the behavior of the process in this interval from 0 to t1. And the random variable t1 to t2, I can arbitrarily give these names t1 up to tk here. And I will get this sort of behavior. Where are we? How many? Tk minus 1 up to t. So from here to here, this is a random variable and tilde tk minus 1 to t. This part here is our nt1. Okay? Because this guy here actually determines this guy here. For arbitrary times in between that I can give names. All right? So, but z1, okay, I have to be a bit more careful. z1, z2, z3 are IID. All right? So now what happens here is that if I look forward in time, say there's an additional t prime here, then what happens here is that this random variable t to t prime here is again, because this is the activity from t onwards. All right, this is the activity from t onwards. This random variable is then independent of all these things. Right, this random variable is independent of this. Because this sequence here tells us about this random variable. And this sequence here is IID, but more importantly, it is independent of all these guys before. Okay, that's more important. Sorry, let me get rid of this. Okay. Okay, just make it look nice. Now we can do renaming. Rename t to be equal to tk and t prime to be equal to tk plus 1. Then what we get is the n tilde of tk plus 1 is independent of all this stuff before. And we are done. Okay. So this part here, I have to be very careful. So this, I rename it to tk. So what I have shown here is that since this is true for all k and for all times t1 less than t2 less than up to tk plus 1, all right, the Poisson process has the Poisson counting process n of t bigger than 0 has the IIP, independent increment process, independent increment property. So let me go through this one more time. Okay, so what does it mean for any counting process to have the IIP? A counting process has the independent increment property if for all integers k, and for whatever way I pick these arbitrary times, these random variables here are independent, this family of random variables. And you don't need to look at all these expressions, just think about this picture here. The activity in these distinct intervals is independent. So the rate of the number of the arrivals in each of these color intervals is independent. On the number of arrivals in each of these intervals is independent. That's the right way to say it. Okay. All right. Theorem. The Poisson process has the independent increment property. This picture is just a guide or proof. And we start from this, which comes from the Memorillus theorem. Okay. If I pick an arbitrary sequence of times here, t1 up to tk minus 1, then this actually determines this. If I know this, I know this thing in the box. Right? If I pick this arbitrary sequence of times inside, then I know this. I know this, definitely. So z1 is also independent of this, because this guy here is a function of this guy here. But the z1 up to z1, this sequence here, we have already shown is ID. So what happens here is that we can replace this by some future happening of the Poisson process starting at time t. So this is independent of that. Now we're just going to rename this as tk and this as tk plus 1. So after renaming, we have this statement here. And since we have this statement, this is true for all k and all times, the Poisson counting process has the independent increment property. Okay. Okay. So you have to remember, and you have to work out problems using the fact that the Poisson counting process has these two properties. And you will have a lot of opportunities to do so. Okay. Okay, people at home, any questions? This is the theorem. questions? This is important. So now we have worked a lot on our X process, which is the sequence of inter-arrivals. We have actually not done a lot because I told you that the X process at the very beginning, okay, here, we can describe our Poisson process in terms of the ID inter-arrival times. We can describe them in terms of the arrival epochs. We can describe them in terms of the Poisson counting process. So the next two items on our agenda are to derive the distributions of the S and the N. That's the next two items on the agenda. Now, there are easy ways to do this, and there are complicated ways to do this. I will show you some easy ways and some complicated ways. Okay? I think the book's way is a bit complicated. My way is better. Okay. So now, the next item on the agenda is to figure out the distribution of Sn. This is the end arrival epoch. That is the next item on our agenda. Then we will talk about NT, which is the most exciting. Okay. So what is the let's not be so ambitious. Let's start with S2. S2 is x1 plus x2, and x1 and x2 are independent. So the xi's are IID. So how do you derive? If you never took my class and you took a good undergraduate probability class, how do you derive S2? This part is actually very exciting, but this is not exciting. This question I'm asking is not exciting. You will do convolution because these guys x1, x2 are independent, and you are thinking about sum. So yeah, convolution. But convolution is very cumbersome. I don't like to do convolution. So we want to do something in a more use your brain way. Don't just do convolution for the sake of convolution. Okay. So now we recall that x1 is equal to s1, and s2, as I already mentioned, is x1 plus x2. Okay. So now our agenda is to figure out the distribution of s2 without going through the pain of convolution. Right. So let us now first describe the joint density of f of x1, s2, x1, s2, the joint density. So by base rule, this is nothing but f of x1, because this is s1, so it's okay. Same thing. Huh? So that's our agenda. We want to figure out s2. Right? So there's a base rule, nothing special. Okay, so we know the distribution of this guy. This is lambda e to the minus lambda x1. So this is this guy here. Aha! Now comes the exciting part. Now comes the part that you have to use your brain. I like to use my brain. So now we draw a picture. This is x1 equals to s1. This is s2. This is 0. So now we have actually described this part here using the green part. Now we're going to describe this yellow part. Yellow is really not a nice color. Okay, but here. Now, what do we have? This distance here is x2. x2 is equal to s2 minus x1. Right? Can see, right? Yeah. So, how do we describe this density? F of S2 given x1, S2 given x1. Well, that is just nothing but f of x2 evaluated at S2 minus x1. Right? What is the distance from here to there? S2 minus x1. What is the random variable of interest? It is x2. So we have this. You agree? You agree? Very good. That's the purpose of having an audience. Otherwise, I'm talking to the Zoom, like no one is going to tell me whether they understand or not. But here I can at least get some nods. All right, so we copy this, lambda e to the minus lambda x1. Now this is also exponential, lambda e to the minus lambda s2 minus x1. But if you do this in your quiz or exam, you will get 90% of the marks. What's wrong? Why am I not happy? Why am I not entirely happy? Because this is not completely true. This is true only if S2 is bigger than X1. Because if S2 is smaller than S1, you get 0, which is the mark that you deserve. Right? So in conclusion, f of x1, s2, x1, s2, we write it properly, is lambda e to the, and you notice here we have something amazing. This part cancels with this part here. Lambda squared e to the minus lambda s2, and here you have to be super careful. You do this, you also not make me feel very happy, because s2 it could be negative. So you have to do this 0 less than x1 less than s2. In this way, we are all very happy. Okay, so notice the following remark. Okay, this joint density or density seems not to depend on x1. This implies that x1 is uniform over the interval 0 to s2 if s2 is equal to s2. Now, if you have a density that seemingly does not depend on a certain value, then it is uniform. For example, you have this density here. So this is x, fxx. So fxx is equal to 1 over a, x between 0 and a. So this seems not to depend on x, so we are uniform. But look at this. This looks more complicated. This expression does not depend on x1, so it must be uniform over this particular interval 0 to x2. Okay, I'm going to get rid of this. This is analogous. Okay, you see this does not depend on x here. Okay, so we'll discuss more about this next time when we talk about conditional arrival densities. Then when we talk about this, you have to be super familiar with conditioning. Okay, but we'll talk about this next time. The point is that it's uniform over this interval. All right. But remember, we are not done. We want the distribution of S2. But now we are almost done. Because f of S2 is equal to integral. We take away the x1 running from 0 to S2, because x1 can range from this. Right? F of x1, S2, x1, S2, d of x1. So now we put in this d of x1, and what we get here is lambda s2, lambda squared s2 e to the minus lambda s2, and this won't make me very happy unless you write this. Okay, so we have derived without convolution pain, without pain of convolution, we have derived the s2. Remember, S2 is x1 plus x2. We have derived the distribution of the second arrival epoch. And this is the name. This is the Erlang density of order 2 with rate lambda. Okay, so that has a name. This density has a name. This density, this one equal to this one has a name. Is the Erlang density. S2 is non-negative. Okay, of order 2 with rate lambda. So what do you think is the Erlang density of order 1 with rate lambda? Erlang density of order 1 with rate lambda. Yes, it's exponential lambda. Remark. Maybe I will create my own notation apply so I don't write so much. Erlang density of order 1 with rate lambda is nothing but exponential lambda. So we call this Erlang 2 lambda. I do not know whether Wikipedia does this, but I think this notation is fine. Okay, so remark the Erlang order 1 with rate lambda is exactly exponential lambda. Okay, good students will check the above via convolution and Laplace transforms or MGFs. Good students will check this. Homework, okay? So we have a simple way, and this is the remark is the painful way, right? Okay. So now we are not done because I told you this part of the agenda is to derive the density for f of Sn. So you can go through this procedure to get f of S3, f of S4. But we are not so painful. Again, we want to do things in a smart way. So clean that we will prove. Let's call this theorem. Okay. F of Sn, this is the nth arrival epoch. Is of course the Erlang density of order n with rate lambda. Lambda and S minus 1 e to the minus lambda Sn divided by n minus 1 factorial Sn bigger than 0. Okay, so remark, this is true for n equals to 1 and n equals to 2. In particular, for n equals to 1, we recover lambda e to the minus lambda S1 over 0 factorial. 0 factorial is 1. So it is exponential lambda. And for n equals to 2, we get lambda squared S2 e to the minus lambda S2 over 1 factorial, which is equal to 1, so I will not put it down. And this is again Erlang 2 lambda. Okay, so it checks out for the first two. This is very ugly. So first two we are okay. So of course, how to do these sort of things when you have n and the first two are okay? The first two we have already proved. There's only one way to do these sort of things. What? Induction. Thank you. So we are going to use induction to do this. Okay, then we'll see something interesting. Okay, so we are going to, so our agenda from now until we take a break is to prove this thing and to provide some interesting remarks. Okay, and when I provide interesting remarks, you are going to appreciate my drawing. I cannot draw human beings, but I can draw 3D pretty well. You will see. Okay. Okay, so I cannot draw 4D. So we're going to prove this theorem. To prove this theorem, we will prove a subplane first. That is joint density. So this is the marginal, right? The theorem is the marginal density of the Sn. Let's look at the joint density. This is the claim. S1 up to Sn, S1 up to Sn. This is a claim. We want to prove it. Lambda n e to the minus lambda Sn. If you do this, you only get half the marks. Because you have to be aware that all the S's must be ordered. All right? All right, they must be ordered. If they are not ordered, if this is not true, the density is 0. Okay, so we will not write that down. Okay, actually, we should be pedantic. Let's write it down. Okay, 0 else. Okay, we be pedantic. Sometimes this is called for, right? Like some, yeah, in the quiz, some people say, Oh, this is obvious, right? So if I agree with you that it's obvious, good for you. If I feel that you should be pedantic, then I'll take away some small amount of marks, all right? But this one is very, very crucial. So we must be pedantic here. So let's prove this subclaim before I prove the big claim, the big theorem. Okay, so obviously there's only one way to do this sort of things. And of course, it's induction. So we assume that it is true for the nth version, and let's do the n plus 1 version. So this is called the induction hypothesis, right? I'm not going to write down the induction hypothesis. Sn plus 1, S1 up to Sn, and Sn plus 1. This is equal to f of S1 up to Sn. What am I doing here? I'm employing Bayes' rule. Sn plus 1 condition on S1 all the way up to Sn, Sn plus 1 condition on S1 up to S1. Yes, Sn. Very ugly. Right, S1, Sn. Okay, so this is nothing but Bayes' rule. So we're going to check out that we're going to check that this actually works for the n plus first version. All right. So now we use the induction hypothesis here. This is lambda n e to the minus lambda Sn. And now we need to use our brains. Okay. So this part here, what's happening? Draw a picture. 0. Sn is fixed, and we are asking what's happening to Sn plus 1. What is this interval? What's the distribution here? It's nothing but Xn plus 1, an exponential random variable. Right? And does it matter what S1 and S2 and Sn minus 1 are? It does not matter. The only thing that matters, all these things are immaterial here. Immaterial. The only thing that matters is Sn. All right? So what happens here is that we have, to be precise, f of Xn plus 1 evaluated at Sn plus 1 minus Sn. That is to be pedantic. Okay? That is equal to lambda n e to the minus lambda Sn. This is exponential random variable, so e to the minus lambda Sn plus 1 minus Sn. And these sort of things must be very beautiful. Cancel, cancel. So this becomes lambda n plus 1 e to the minus lambda Sn plus 1. We require Sn plus 1 to be bigger than Sn. But for this formula to hold true, we need that Sn is bigger than Sn minus 1, S2, S1, 0. For this to hold true. Now, I know I say I'm pedantic, right? But really, we cannot have this equality here. But it doesn't really matter too much. These are continuous random variables. Okay, so this is the case for the joint density up to and including n plus 1. So this claim checks out. This claim is true. Subclaim is proved. So this proves the subclaim. Okay, because this form here is the same as that of the subclaim here. So now we want to prove the theorem. By the way, any questions on this subclaim? Any questions about this proof? This is super important, especially this picture which you should have in your head. Okay, people in the Zoom, any questions? People not in the Zoom, any questions? I do one more calculation and we'll take a break. Any questions? Again. Maybe, oh, no questions, good. All right. I can only see Zheng here. All right, so now let us do n equals to 3. Let's prove the claim for, this theorem here. So let's copy this theorem for n equals to 3. In my notes, my cutout notes, I did for n equals to 4. You can do it whatever. You can see the pattern. So we'll prove this claim for n equals to 3. Okay? Otherwise, there's too much for me to write. So the way to do this is, of course, to integrate out S1 and S2 from the joint S1, S2, S3 is to integrate out. But I caution you that this integration is not so simple. Okay? So f of S3, there's the integral over what? Over the set S1, S2, such that 0 is less than S1, less than S2, less than S3 of the joint density S1, S2, S3, ds1, ds2. Okay? But we have to take extreme care here. The inner one is the integral from 0 to S2 of the lambda 3 e to the minus lambda S3. This from here to here is from the subplane. Joint density. S1, S2, 0 to S3. Why? Why did I write it like this? Okay, because here inside S1 can only range from 0 to S2. Okay, and for the outside, this because S2 can only range from S3 to 0. S2 must be less than S3 in particular. Okay, there's no restriction on S2 here for the left hand side. So you see the limits of the integral here are super important. Okay, so that's why it's a bit tricky. And this part here is done too quickly in the book. I basically wrote this out. I wrote out this whole proof for you carefully. Okay, in my lecture 5 notes. So after we perform this integration, we have lambda cubed. The inner, the one in the parentheses, can be controlled by minus lambda S3, the S2, and then this is nothing but S2, S3 cubed. S3 squared over 2 lambda cubed e to the minus lambda S3. S3 is bigger than 0. And this is the Erlang density of order 3 rate with rate lambda. So we prove this for the n equals to 3 case. For the general case, you can use induction. All right. But induction is nice. But there's a geometric meaning behind this as well. Okay. So the remark for n equals to 4, see lecture 5.pdf supplementary notes. Okay. Why do we have the factor? Okay, before I move on, any questions here? Any questions from the people at home? So the objective here is to find the end arrival epoch. The end arrival epoch. Okay. That's my objective. Maybe I can just short this. Yeah, that's better. My objective is to find the distribution of the end arrival epoch. I go through the joint distribution first. The joint distribution, then I integrate out. When I integrate out, I must be very careful with the limits. You don't put infinity here, very wrong. Okay? Then you integrate this carefully, like as follows. Okay? So if there are no questions, any questions from the audience here and from the Zoom people? So there exists a factor in general, Sn n minus 1 over n minus 1 factorial, because the volume of the region S1 up to Sn minus 1 such that 0 less than S1 less than is exactly or precisely Sn n minus 1 over n minus 1 factorial. So this is very abstract, if you ask me. So let's do a example. N equals to 2. So the region is what? The set of all possible xy's such that 0 is less than x, less than y, controlled by S2. What is the size of this region? Let's draw it. Okay, so this is the x-axis, this is the y-axis, and this is S2. This is S2, and we are in this region here that x is smaller than y. Right? Now, the square has what area? S2 squared. This part has area S2 squared over 2. This for the case n equals 2. Okay? This for the case n equals to 2. That's the reason why we have this extra factor. So for n equals to 2, this specializes to S2 squared over 2. Also, this n equals to 3. This is n equals to 3, I'm sorry. S3 squared. S3 squared over, it should be S3. Right? S3, am I right? 3 minus 2 is 2. 3 minus 1 is 2. 2 factorial is 2. So this is true. This should be controlled by F. My notes are incorrect. S3, S3. n equals to 3, right? Yeah, so you have this extra factor here. And this extra factor is explained here. Okay? So now let me consider even a more complicated scenario. N equals to 4. So the region is in 3-dimensional space, x, y, z less than S4. Aha. So what do we have here? All right, so basically we have this picture. So this is z, this is y, this is x. And we are only allowed to go up to S4. I promise you that I will draw a very nice picture, right? So we have a cube, right? What's the size? What is the volume of the cube? It's basically S4 cube. This is all S4, right? But not all of this entire cube is of interest to us. We are only interested in this sort of behavior. So where are we located? Now, if you keep track of this, then you are located here. Oh my gosh, this is not very beautiful. This part here. This little, what is this called? Triangle that is like a 3-dimensional triangular prism, right? So we are only in this region here. What fraction of the entire cube is satisfied? Is this equation satisfied? What entire fraction? Okay. Now, a very easy way to see this is that you can arrange x, y, z, x less than z less than y. This is another region. Now we have y less than x less than z, y less than z less than x, and we have z less than x less than y, z less than y less than zx here. We have 6 different types, 6 different combinations, 6 different regions, right? So the volume of this region is equal to S4, how many? Cubed over 6. And this is exactly S4 cubed over 3 factorial. 4 minus 1 factorial. Is this clear? This picture can be drawn better. But you see the point. I'm only interested in this ordering. But there are 5 other different orders by symmetry. Each one of these takes up the same volume by symmetry. So here, the entire box here has how much volume? S4 cubed. So this part that I drew, but not so beautiful, it's more beautiful in my notes, is S4 cubed over 3 factorial, which is S4 cubed over 6. All right, so that will be the the coefficient, if you wish, of the Erlang density of order 4. All right, this is a simple case for Erlang density of order 3. Okay, so this is Erlang density of order 4. All right, so maybe we can take a break right now. And when we come back, we will talk about the density or the distribution of n. Okay? Yeah, 罗子健. Yeah, so S1 is denoting, it refers to X, Y refers to S2, and Z can only be bounded by S3. Okay? Z less than equal to S3. Okay? So we take a 10-minute break. We come back at 38, and then we'll talk about the distribution of the counting process. Okay? Right. So I will stop the recording for the recording. Okay, can the Zoom people hear me? Okay, great. So what is our agenda now? Our agenda now is to prove the distribution of NT, the counting process at time t. Okay. The PMF of NT. Recall that NT is the number of arrivals up to and including time t. Okay. So, theorem. So we had the Poisson process that was defined, at least for our class. We defined it starting from the IID exponential process, exponential distribution, the interarrival times. If you take another class on Poisson processes, they may start from this. All right, so we start from x's, which I find is the most natural. I think Ross' book, which I also put in Luminous, right, starts from this. Then it proves the counting process. It proves the interarrival times. But that's also fine. There are many ways to define a Poisson process. We started with the exponential distribution. I think that's the easiest. But from the exponential distribution IID, we want to show the following theorem. Okay. Consider a Poisson process with rate lambda. So the PMF of NT, this is a discrete random variable, is a Poisson random variable with mean or rate lambda t, i.e. P of NT n is equal to e to the minus lambda t to the n over n factorial. And I think in our homeworks and so on and so forth, we have played with this PMF several times. All right. So the book produces two proofs of this result. I will go through the first proof, and I will supply my own. Okay, that is independent of the two proofs in the book. Okay, so this is a statement. Okay, we first started with the exponential IID. Xi's are exponential. IID and exponential. We somehow, to some case, got the distribution of the nth arrival at fork. And now we want to try to get this. So that's the story up to now. Okay. So we have this and we want to get this. So we will be making use of this relation here. By remembering that actually we got this through this. Okay. So that's the story. Okay, so the first proof is as follows. Each one of these proofs illustrates a slightly different point. Okay, but for the first proof, you need some additional notation. That's why I don't like it. All right, because I need to teach you something else. Okay, so we say that a function g delta is equal to little o, but this is little o delta. If, actually if and only if, right? How to say? Limit delta equal to 0 of g delta over delta is equal to 0. For example, so this g delta is a family of, sorry, this o delta, little o delta, is the family of functions that decreases to 0 faster than linearly. Okay. For example, G delta is equal to delta squared is in little o delta. This is some computer science notation. Okay. Computer science thing. For example, G delta is equal to delta is not in little o delta because its limit doesn't go to 0. Okay. Here's some computer science thing that is very useful when we want to be very relaxed about saying things. Okay, so the proof one requires the use of this. Okay, let's consider the event t less than Sn plus 1 less than t plus delta for some small delta. So what is the picture? All right, what is the picture? We have that Sn plus 1 is here. It is strictly bigger than t, and this interval is very small. It's only of size delta, and there have been n arrivals here already. Okay, so this is Sn at 0. Okay, so that's the picture. But this interval is very small. I blow it up, otherwise there's not enough space for me to draw. Okay, so we are going to compute this in two different ways and equate them. We're going to compute the probability of these two intervals in two different ways. So probability of t less than Sn plus 1 less than equal to t plus delta. Well, that is nothing but the integral from t to t plus delta of f of Sn plus 1 tau d tau. Well, that's the meaning of probability, right? So if delta is very small, because this density is continuous, right? We can write down the following. F of Sn plus 1 t is t, and delta plus little o delta. That means, okay, what is the meaning here? This is like Riemann thing, right? So this is some nice density, and we are trying to evaluate this from t to t plus delta. So we are trying to evaluate this area here. And so this is the value of this density at t. Okay, how to evaluate this area here? Well, we can approximate this area. Approximate this area by means of f of t times delta. And the remainder term is this little o delta, just to be precise. Okay, so if this density is continuous, we can do this. Okay, but you don't need to know what is continuous. So just believe this. All right. Right. So this is one way of evaluating this probability. Okay. Another way of evaluating the same probability is noticing what is the meaning of this probability. So look at this. What this means is that probability is the same as the probability that there are n arrivals in 0 to t and one arrival in the small little strip t plus delta. Right? There must be n arrivals here and exactly one arrival here. Right? So the one arrival here and n arrivals prior. That's the picture. Can you see? Right, that's the meaning. Okay. So these two parts are, these two events here, the green event and the red event are, can anyone tell me? They have some property. The green part is an event, the red part is some event. There's some property. You see these two, I wrote this very nicely, right? This interval and this interval are disjoint. So whatever happens here is independent of whatever happens here. Do you agree? So we can rewrite this as the probability of n arrivals in probability 1 arrival. This is the meaning. independent. Okay, but this is exactly the meaning of this. That the number of arrivals in the interval from 0 to t, that is this random variable. That is the variable taking on the value n. Okay, and what is the meaning of this? This is nothing but integrating the n plus first inter-arrival time from 0 to delta. We must arrive in this interval, 0 to delta. Okay. One arrival, n arrivals from here to here, and one arrival from here to there. So this is the top. One arrival from. Let me just put x, f of x. This is not f of x n plus 1. This is one arrival means f of x, say tau d tau. Exponential random variable. There must be one arrival in this interval. Okay, so let's write this. Let's copy this down. And this is exponential random variable. So we have this. Integrate this from 0 to delta of this. Okay, now I'm going to do this calculation by the side here. So this is minus e to the minus lambda tau, put in delta to 0. So this is 1 minus, how much? So e to the minus lambda delta. Yeah. So by Taylor series or Taylor's theorem, this is lambda delta plus little o delta. Why? Because this is exponential. When the argument is very small, it behaves e to the x, behaves as x. 1 plus x, right? E, something like this. E to the x behaves as 1 plus x, when x is small. So this 1 and this 1 cancel, and we have this behavior. Okay, this can be verified by Taylor series or Taylor's theorem. So we can plug this into here, lambda delta plus little o delta. I don't really like this proof because you need to know a lot of other things. Okay, but this is the first proof, and so we have two ways of calculating this probability. And so because these two probabilities are the same, so these two calculations must coincide. Lambda delta plus little o delta must be equal to what we had above here, which is this quantity here. But we know the Erlang density. So substituting the Erlang density into here, we get that P of NT, and I'm going to ignore the little o now. What is the Erlang density? The Erlang density is lambda to the n. This is Sn plus 1, right? So Sn plus 1, you have lambda n plus 1, t to the n, e to the minus lambda t over n factorial delta. This is the Erlang density. I'm just copying down what we derived just now. That's why I say we go from the x to the s to the n. All right. So now we can actually take away this delta because it is not 0, but it's just some small number. And then we can divide through, and magically, voila, we get Poisson. Magical, right? This is the first proof. This is the book's proof. Okay? So, good for them. Here we make use of actually something important, the independent increments property. Right? Because this part here, this is an increment of this part. It's incremental. And this increment is independent of the past. So we make use of this independent increments property here, IIP. We make use of some notion of continuity of this thing here, but this is basically how you evaluate this little area here. You evaluate this area by height times width, right? Something like this. And then here we make use of the fact that this is exactly this definition. And to have one arrival in this small little strip, you basically integrate the exponential density from 0 to delta, and this quantity here is actually lambda delta. Okay, so you need to know that, but this requires a little bit of analysis, like Taylor.
I think the equality on top isn't exactly no.
The independence.
An arrival on arrival one, right? Above? Sorry.
This one?
Yeah, okay, that equality sign is not strictly true.
Why?
You still need to have a O delta term. Because you have Sn plus 2 or Sn plus 3 inside delta. But it is
probably
OD factor, right?
Yeah, it's probably very small. Let me see. What does the book say? Sn plus 1 is between
Sn plus 2 is also
Sn plus 2 could be inside, right?
Yes.
Yeah, but if, okay, maybe you're right.
But then you'll have to section it into delta 1 plus delta 2. Then the result will be O delta square. Or delta less than 1.
Yeah, maybe this is not quite right, but we can adjust this by a little O delta like that. But I have to think about it. If, of course, this works out, if delta is very small, this O delta does not affect us too much, right? But indeed, it seems like, at least when I'm here and I'm facing the crowd, this could have been 2, because Sn plus 2 could be inside this small interval as well. But I'll think about it and I'll get back to you. Okay. But in any case, you see the structure of this argument here. I don't really like this because it has too many approximations for my liking. So let me show you my proof. Okay. In any case, here what we have shown is that modulo these approximations, we have that nt is a Poisson random variable with the mean lambda t. Okay. So this one I didn't type out, I didn't write out. I just thought about this proof this afternoon. All right, so let me just show you. Okay. So this is not in the book and not typed out. And this is the first time I'm doing it. All right, so hopefully correct. So proof 2. We want to prove that this the Poisson distribution actually characterizes the Poisson counting process at time t. Okay. Now recall that the event nt bigger than n, you might want to take this down, but I will also post these handwritten things. We showed this. To me, this is the most straightforward. We showed in some detail, these two events are the same. And in your homework, you also prove this. This is true. So to me, this is the simplest thing. Okay. And we need one fact, which can be shown by integration by parts. Here you also need integration by parts, but maybe that's not so difficult. You integrate from this to that, xn minus 1 e to the minus ax dx. You can integrate this by parts. N minus 1 factorial over an into 1 minus e to the minus ab. Of course, if I want you to do integration by parts, I will give you this sort of formula. But I'm saying that you can look this up on Wikipedia. Okay, it looks a bit involved, but let's prepare this first. Here there are no approximations whatsoever. This is true, and this can be verified by induction and integration by parts. You assume that this is true, and then you do the next one. Okay. And for n equals to 1, this checks out. Okay, this is easy. Okay. So we need this, and then we can show what we want to show. Okay, so let's consider probability of nt bigger than or equal to n. That is nothing but probability of Sn less than equal to t. Because the two events are the same. Okay. So I feel that this is a more organic way of doing things. You integrate from 0 to t of the length, right? Lambda n s n minus 1 e to the minus lambda s over n minus 1 factorial ds. Agree? That's the length I plugged it inside. Length I plugged it inside. All right. So these things are constant. Lambda n over n minus 1 factorial is constant. And this part here requires our fact. All right, this part here, just put on the fact. Okay, so the fact is very convenient. After you use the fact, you will have this part here, n minus 1 over an. The a is actually lambda, so we have this cancelling very beautifully. See beautiful cancellation. And 1 minus e to the minus lambda t, sum up to n minus 1, lambda t, the ab is lambda t over I factorial, I equals to 0. Okay, so if you believe the fact here, you believe this, and you will be very, very happy to get rid of all these things. Beautiful. This is my proof. No approximations, okay? So we're not done yet because we want equal n, right? So we do one more calculation. Why don't we do probability nt bigger than n plus 1? Okay, yeah. You just replace the n by n plus 1. So the top becomes n. Okay, good. So our PMF, this is equal to n. That's what we want. But this is exactly greater than n minus nt greater than n plus 1. Right? The picture is as follows. This is n plus 1, this is n plus 2. This part here is everything up to here. This part here is you take all this part here. So you're left with your lovely n, which is this part here. I'm taking away. So what will we do? We take this part here. This is this right hand side, and we take this here, and we take the green and we take the minus, green minus the orange. What are we left with? We take the green minus the orange. What are we left with? Beautiful. E to the minus lambda t. We are left with the n term, lambda t to the power n over n factorial. So this is my proof. No need to talk about little o delta. Okay. And what are we doing here? Because we put in so much effort last time to prove this thing here, why not we use it? Math is about building on what you already know. So you need to know this fact, unfortunately. Okay, but this can be done through integration by parts, which I'm not going to do. If I do integration by parts here, with probability 1, I will make a mistake. So we equate these two things. These two events are the same, so their probabilities are the same. But we know that Erlang put inside here. Now some constants can be brought outside. What is important is this part here. This part here can be evaluated using the fact. If you track all these things carefully. Now we increment by 1 here. Then this n minus 1 becomes n. Then we subtract to get the PMF. And voila, we get the Poisson. The people at home, the Zoom people are very cool, right? So this is my proof. Okay, anyway, I thought about this afternoon. I don't know what the proof in the book. The second proof in the book is also a bit too complicated for me. Okay, so in conclusion, NT is Poisson lambda t. An expected value of NT is equal to lambda t. Okay? Yeah, the people at home never agree with me. Right? Sleeping. Okay, anyway, so you see there are two proofs here. You can choose whatever you like, but actually, now I'm thinking of some questions for quiz 2. Maybe something like this will come up, right? Something like this. But I still need to think about what can be done. Right? There are not many things that can be done apart from asking you, okay, so you have Poisson process. So how long do you have to wait to get your first bus? How long do you have to wait to do this and that, right? So maybe they will have some computational questions, but I also want to test on analytical questions like these. Okay. Okay. Now Luo Zijian agree. Cool. All right, so now I'll talk about some other characterizations of Poisson processes, and then I'll talk about splitting and combining. Splitting and combining won't take too long, right? So we have 1 more hour. Let's see. Okay, alternative definitions. So as I mentioned, our treatment, how we did it was that we started off with the interarrival times that were IID. But you could very well start with the counting process that is Poisson. All right. You could very well have started with that and then derived other things. That was not our approach because I follow the book. But you can also do the following. This is a perfectly legitimate treatment. A Poisson counting process, NT for T positive, is a counting process such that NT is Poisson lambda T. By NT sim Poisson lambda T, I mean that for every fixed T, NT is a Poisson random variable with mean lambda T. All right, that's my shorthand notation. Such that this family of random variables has such that this N, maybe this English is not very good, has the stationary increment property and independent increment property. Please read this carefully. Okay, why do I want to ask you to read this carefully? It's not for fun, right? Because you would think that if I do the following, a Poisson counting process is a Poisson counting process such that this, and we get rid of this. This is a legitimate definition. You might think this is okay. We can define the Poisson counting process just by NT distributed as Poisson lambda T. But in one of the exercises in the book, which I didn't ask you to do because it's too technical, but you're free to do it if you want, all right? If you define a Poisson counting process without this last line here, it will not be, it will not yield the desired properties. Or for example, the xi's being IID lambda, IID exponential. There will be something that breaks. Okay, so having the stationary increment property and having the independent increment property is important to define a Poisson counting process. Okay, so we really need this. So this is another definition of a Poisson counting process that we need to know. But the punchline is that you should know what is the stationary increment property and the independent increment property. So we also know that this is yet another definition. Okay, this has the same distribution of this as this by the stationary increment property. Okay. So if we have a process that looks like the following, the probability of n t to t plus delta equals to 0 is equal to 1 minus lambda delta plus little o delta, and the probability that n t plus delta equals to 1 is equal to lambda delta plus little o delta, and the probability that n tilde t plus delta bigger than or equal to is equal to little o delta. So that specifies a Poisson, that specifies a certain process, right? That specifies a process. And I just want to remind you that, for example, for this, okay, for star, what do we really mean? If the left-hand side is some A delta sequence or some function in delta, what star means is that this is A delta. It says that A delta minus 1 minus lambda delta absolute value divided by delta tends to 0 as delta tends to 0. I guess okay. So that's what star means. That's the meaning of little o delta. Well, intuitively, right, what it means is that if I have a super small interval, the chance that there is no arrival is 1 minus lambda delta. The chance that we have one arrival is lambda delta. The chance that we have 2 or more arrivals is super small, and you don't worry about it. Okay? So you have this picture here. T plus delta. This interval is very small. The chance that there's one arrival here is equal to lambda delta. 0 arrivals, approximately, is 1 minus lambda delta. So what is left? Nothing left. So you cannot have more than 2 arrivals. You cannot have more than equal to 2 arrivals because there's no more probability left, right? So that's what these 3 equations are saying. Okay? So just to summarize, let's call it star. All right? So we can define another way of defining a Poisson counting process is a counting process that satisfies star and satisfies at the same time the stationary increment property and the independent increment property. So, you know what we did just now? The other definition? We actually specified the distribution of NT at each T, Poisson lambda delta, Poisson lambda T. And we added on the stationary increment property and the independent increment property. Now we are not talking about this anymore. Oh, sorry. Now we are not talking about the fact that we have this distribution. We are just specifying what happens in a small interval. Okay? And if you satisfy the properties of this small interval, having more than or equal to 2 arrivals, infinitesimally small. All right? 1 arrival lambda delta and 0 arrivals 1 minus lambda delta. That suffices. That this condition can actually replace the Poisson condition. All right, but you cannot avoid the SIP and the IIP. All right, so this is some fact, okay, that one can prove, but I won't ask you to do this. I don't think I asked you to do this in the homework. Okay, so we still have time, and I want to talk about now. I want to talk about relating the Poisson process to the Bernoulli process. You might think that the Bernoulli process is very different from the Poisson process, but actually it's not. Oh, before that, any questions? Any questions on this?
Do you have an easy example for something that is a Poisson in lambda T, but doesn't satisfy either SIP or IIP?
And then breaks the whole thing. Yeah, there are some in the book, but I cannot recall at this point. Perhaps I will do this example next time if I have time. Yeah, if people are interested. But next time, what I plan to do next time is actually I want to finish conditional arrival densities, and then I'll do some practice problems to finish up the discussion of Poisson. But if people are interested in this, I will do this Gallager problem 2 point something that shows that if I have just NT Poisson lambda T and I don't have the SIP and IIP or one of them, then something breaks. I cannot remember the example right off the top of my head right now. Okay, I do not know how to construct this. And what will break? Okay. So, Zheng Tian, right? How is star derived? Actually, what I want to say is that let us consider a counting process that has property star. Just consider a counting process that has this property that in a small little interval, you cannot have more than or equal to 2 arrivals. This is a condition. Let's call this condition star. Now, assuming that our counting process has condition star and it has the SIP and IIP, then this process is equivalent to the process that we have constructed, which is the Poisson counting process. Oh, Zheng Tian is convinced. Good. Okay, good. So you see there's a logic here. This is a condition. All right. So now I don't want to prove this. In previous years I proved this, but I don't see that there's a big need to do it. Anyway, you have done it in the homework. Poisson process is the limit of shrinking Bernoulli processes. Okay, so this is very interesting. You know what is a Bernoulli process? The Bernoulli process is nothing but a sequence of ID random variables or a sequence of coin tosses. Okay, so here all the yi's have alphabet 0, 1, and the probability that yi is equal to 1 is equal to p, and the probability that yi is equal to 0 is equal to 1 minus p. Some people call it q. Doesn't matter. And yi equals to 1 signifies that there is an arrival in time slot I. And of course, if you have yi equals to 0, then you don't have an arrival in time slot I. Okay, so hopefully this is clear. No arrival in time slot I. So this is nothing but a Bernoulli process. But what we are going to do is to now talk about what is the meaning of time slot. I have not defined what is time slot. All right. So we are going to consider now a sequence. I love sequences. I'm an analysis person. Of Bernoulli processes indexed by J. Okay, so the picture is as follows. All right, you have this Bernoulli process, and you have a certain time slot. Now we are operating in discrete time, which is simpler for some people. Okay, so this is the I time slot. Okay, and each time slot is of size delta equal to 2 to the minus j. So each time slot is of size delta equal to 2 to the minus j. I just said this, I make it, and I write it down. Okay, understand? So this is the first time slot, the second time slot, the third time slot, and so on and so forth. And yi equals to 1 means that there is some arrival in the ith time slot. Okay, very soon we are going to let j tend to infinity. So if the time slot is very small, very soon I'm going to let j tend to infinity. Okay. Now we are considering a sequence of Bernoulli processes indexed by j. For the j Bernoulli process, let the arrival rate or the probability of success p, I don't want to call arrival rate, let the probability of success be called pj, which can be called lambda 2 to the minus j, which is lambda delta. Now it seems like we are going to make some connection to the Poisson process because we see this lambda delta. Right? Now we are considering a sequence of Bernoulli processes. Okay? And each Bernoulli process has a certain time slot size, 2 to the minus j. And for the j Bernoulli process, the success of landing in a certain slot is lambda, probability of success is 2 to the minus j. Why do we design it this way? Now, we live in continuous time. We don't live in discrete time. So let's say this is 1 second. This 1 second here. This from here to here is 1 second. By considering this parameterization, the arrival rate in 1 second is constant. Right? So suppose this is like 1, 2, 3, 4, 5, 6, 7, oh sorry. Suppose j is equal to 3. Now there are 8 time slots here. J is equal to 3. There are 8 time slots here. This is 1 second. On average, how many arrivals inside here? Lambda, right? Because you have this 2 to the minus j multiplied by lambda 2 to the minus j. Lambda, right? Lambda arrivals in this green big time slot for 1 second if j is equal to 3. So the arrival rate is constant by this parameterization. Okay. So a comment is that the arrival rate is constant across j. Right? You agree? Because we parameterize things like this, the chance that I actually drop into a certain box here is lambda 2 to the minus j. But the box size is also shrinking. The chance is also shrinking. The box size is shrinking with increasing j. That's why it's called shrinking Bernoulli processes. But the chance you drop inside the box is also shrinking like 2 to the minus j. So for a fixed length of time, like 1 second, right? The chance, the rate of arrival in 1 second is lambda. Okay, right. Right, I've already talked about these two things. So this is the Bernoulli counting process. So we can define the Bernoulli spelling. The Bernoulli counting process for the J, the J Bernoulli counting process. Let's talk about NJT. Is equal to sum yi I running from 1 to T2 to the J floor. Why do we need all these very painful things, right? So what we have here, oh, we still have friends joining us. Maybe they got locked out. Okay. So why do we need all this? So I will draw a picture. Okay, so we have this, say we have 8 time slots. All right, so these are 8 time slots. You have y1 up to y8, y2. That's good enough. And say we are j equals to 3, the third Bernoulli process. So this length is 1/8, 1/8, 1/8. These are meant to be equal. So now this is continuous time, right? And so now, right? Suppose my t is equal to 7/8. All right. Then we are looking at this part, this point here. What is the maximum number of arrivals we can have? 7. Right? If you are a direct rational like this, 7/8, you reach your bottom, your denominator is a power of 2. Now, suppose on the other hand, what color do you like? Maybe this color, okay? T is equal to 9/10. This is not a direct rational. Then we are here, right? Somewhere here. So what's 7/8 is 0.875, right? Something like that. This is 0.9. How many arrivals can you have? Still 7 only. Still 7. That's why we need this floor here. That explains this floor thing here. All right, because we are taking this, okay? So for example, if we are 9/10, we are multiplying by 2 to the power 3, taking floor. This should be 72/10 floor, which is 7. Understand? So we can have at most 7 arrivals. That's why we need this floor. We cannot have because we are operating in discrete time, we need to cut it off, right? That's what we are doing here. So the Bernoulli counting process for the J Bernoulli counting process, it is exactly this quantity here. Okay. So in particular, the distribution of NJT and is the total number of arrivals you can have is this. Choose n, p to the n, 1 minus p to the floor t2 to the j minus n, where n can run from 0 to t2j. Bernoulli random variable with this number of trials and probability of success probability of success is equal to lambda delta, which is lambda 2 to the minus j. Okay, so the theorem is as follows, which is very interesting. Consider the above constructed of shrinking Bernoulli process with constant rate. Sequence of shrinking Bernoulli processes with shrinking rate, with arrival probabilities lambda 2 to the minus j equals to p, and slot size 2 to the minus j. Okay, then fix t and fix n. Right? What we have is that if I take the limit as j tends to infinity, that means I make the time slot super small. And that also makes the probability of you landing in a time slot very small. Okay. Now I look at the chance that the Bernoulli process takes on the Bernoulli process takes on the value n. Then we recover the Poisson distribution. This is e to the minus lambda t to the n over n factorial. N can be any arbitrary non-negative integer. Okay, so I'm not going to go through this proof because we have already done it. Similar to a problem in homework 4. Actually, this has a name. This is called Bernoulli Poisson theorem or something like that. So this is a sequence of Bernoulli distributions. This is a sequence of Bernoulli distributions. And with the correct scaling, you can actually approximate the Bernoulli distribution by Poisson distribution. Okay, so this is something that I will not prove because you have already done it through a sequence of approximations in homework 4. So this is yet another construction of the Poisson process. Okay. Very good. Okay, so I want to talk about two more things. Splitting and combining. And then we'll call it a day. So this theorem here is very nice because if you have very small probabilities and very large n, then oftentimes it is very cumbersome to evaluate these sort of things. Very small probabilities, very large n. So we can approximate this by a Poisson. All right. So that is the this thing has a name, right? It's called the De Moivre Laplace something. I think I learned this before in JC. So this, but we never proved this. So this is the proper proof of this is in homework 4. But basically, you have a bunch of Bernoulli random variables, a Bernoulli distribution, and you approximate them by this closed form formula. Because this thing is a bit hard to deal with. Right? Any questions? Any questions here? Any questions from the people at home? We have more than enough time to talk about the remaining tough stuff. Zijian, any questions? Okay, so people at home are fine. Oh, good. You talk to me. All right. So, last thing I'll talk about is the following. Very exciting. Combining and splitting of Poisson processes. Okay, so let's talk about combining first. This is not too difficult. All right, so we have these two Poisson processes. N1 of t and N2 of t. They are independent. All right, and this has a rate lambda 1, and this is rate lambda 2. Okay, so now we consider the sum process. N of t equals to n1 of t plus n2 of t. Okay, so what are we trying to do here? What is the story that I can create? So now I have people walking into my shop. All right. And I'm starting my counting process. There are two types of people in the world, men and women. This is a bit politically incorrect because sometimes there are third genders also. But say there are only two genders, men and women. So the men come into the shop according to a Poisson process called, the man is M. And the women, let's use red, women here. So I want to understand the rate at which people come into my shop, regardless of what gender they are. Okay, so that's the story. So let's get rid of all these things. Okay, so we want to consider the sum process, and we want to talk about some properties of the sum process. Okay, fact. Maybe you can call it a theorem. The sum process, that is the total number of people that work in my shop, regardless of their gender, is a Poisson process with rate lambda 1 plus lambda 2. Seems very unsurprising, right? Very, very unsurprising, people at home. But actually, the proof is not so simple. I'm going to give you a half proof. The rest is a bit. You need to fill this in, all right? So remember that many pages ago here, we showed that we argued that all that suffices to show that something is a Poisson process is three things. We can show, as long as we can show this equals to 0 is 1 minus, essentially 1 minus lambda delta, and equals to 1 is lambda delta, and greater than or equal to 2, small. Then we are good. What I said is not correct. What am I missing? What am I missing? It's not the third gender, all right? It's not the third gender. We only have men and women in the world, say, okay? But what am I missing? Suppose I prove these three things. This, I thought, according to Ma Zhengtian there, this is condition star. If I manage to prove this, am I done? Exactly. I'm only going to prove this. You can complete the proof of the stationary increment property and the independent increment property. Okay. So as long as I prove this, I'm done. So let's start. So let's start with this part here. Okay. Because we can illustrate some very interesting things here. So let's try to prove this. So this is equal to 0. How do we do this? This is probability. Now, if there are no people to walk into my shop from time t to time t plus delta, how many women walk into my shop? No people walk into my shop. How many women walk into my shop? No women, right? Also, no men walk in my shop, right? So n1 of t and n2 of t. You can put intersection if you want. Right? No men and no women. Now what can I do? The men and the women are not related. They are not boyfriend, girlfriend. They don't walk into my shop together. So they are independent. So we can have, this is split into independent. Right? Okay. But each one of these guys here is a, not guys, guys and girls. Right? The men and the women are Poisson processes. So this guy, this term here is 1 minus lambda 1 delta plus little o delta. 1 minus lambda 2 delta plus little o delta. Right? Because these men and women are Poisson processes with rates lambda 1 and lambda 2 respectively. So we're going to multiply this out. 1 minus, this is the important part, plus you will have terms in delta squared. You will have terms like that. But then we are going to just ignore all this and lump them into little o delta. Okay? So this checks out if I call this lambda. Right? Now, probability that n tilde t plus delta equals to 1. Now one person walk in my shop. How many men walk in my shop? Could be 0 or 1, right? So that is n1 tilde of t plus delta. Let's say the women, ladies first. All right, 1 is ladies. No lady walk in my shop, and 1 man walk into my shop. Okay, or so this is an event. Now ladies first, right? 1 woman walk into my shop, and no man walk into my shop. Right? Okay. Okay. Now let's call it event A and let's call it event B. Then does A intersect B equals to empty set? Yeah, it's empty set. So these are disjoint. So we can just add up like that. Probability that, so that I don't write so much. So we have this. This is equal to this, and plus probability this. Okay? So we can add this up together. Now we can exploit independence. Okay, this is probability of n1 tilde t plus delta equals to 0 multiplied by probability n2 tilde t plus delta equals to 1 plus the other part n1 tilde t plus delta equals to 1 probability n2 tilde t plus delta equals to 0. So now we have plugging all this in, lambda 1 delta. To be precise, we need all this little o delta, but I'm not going to write down, okay? And this part here, this second part here, this is 1 minus lambda 2 delta. And this is lambda 2 delta, 1 minus lambda 1 delta. Okay, so where do all these terms come from? This one comes from here. Okay, so this one comes from here. You can track all these because in the men process and the women process, they are themselves Poisson processes. Okay, so they have these properties. The good thing here is I never run out of colors. Right? So we have all these terms tracked. Beautiful, right? So after we multiply this out, we get lambda 1 plus lambda 2 delta plus little o delta. We have a bunch of quadratic terms that I can all merge into a little o delta. And if I call this lambda, then I check out the second property of star. Okay? And the third property is that the probability of the number of men plus the number of women is bigger than 2. But this is equal to the probability that the number of men is 0. Number of men plus number of women is 0 or 1. But we have already 1 minus 0 means 1 minus lambda delta, and 1 is lambda delta and plus little o delta. So that leaves us with little o delta only. So property star is satisfied with lambda equals to lambda 1 plus lambda 2. I check the 3 properties of star, and the 3 properties of star are satisfied. Okay, this is not the end of the story. Also need to verify SIP and IIP. But this should be possible based on the stationary increment property and the independent increment property of the underlying processes. Okay. So after we verify this, which I'm not going to do, we show that NT is a Poisson counting process with combined rate lambda equals to lambda plus lambda 2. So unsurprisingly, the total number of people that come into my shop, regardless of their gender, is a Poisson counting process with the rate being the sum. But notice that this proof here requires something. Requires that the number of men and number of women who come into my shop be independent. If they are not, all bets are off. Like if a man and a woman hold hand and come to my shop, sorry, this proof doesn't work, right? So you see, this is a partial proof of the case of combining of Poisson processes. Okay, so we have this N1 of T, N2 of T. You form a new process with rate lambda if these two are independent. And by independent, I really mean that for all times. Independent. Okay. Right. We have 20 more minutes for me to prove the last thing I want to prove. Any questions before I prove the last thing I want to prove? Remember this picture. Any questions? Everything good? All good now, but this was like 13 minutes ago. It was all good 13 minutes ago. Yeah, anyway, okay, there are many other ways to prove this, but I'm not going to do it. Okay. So I'm going to talk about splitting. Right? Okay, last thing I'm going to talk about is splitting. All right. There are two other ways to prove this. You can read the notes, okay? Or you can read the book. But it's important to know the result, okay? So now, dual to this picture here, we have the following. What is the story? Last year when I taught this, maybe about 3 years ago when I taught this, I gave the story. But I need to update my story now. These things have stories, okay? So let me talk about the story. So these are the people who walk into a voting booth. Voting booth, vote. Then these are the people who voted for Joe Biden. And these are the people who voted for Donald Trump. Why voting booth? Because people walk into the voting booth according to a Poisson process. All right? But you do not know who they vote for. Okay, even if they wore a hat of Make America Great Again, you do not know whether they are going up or they're going down here. All right? There's some probability. But whenever someone walks into a voting booth, a coin is tossed. And if coin turns out heads, he or she votes for Joe Biden. Otherwise, he or she votes for Donald Trump. So now we are going to collect those people who voted for Joe Biden into its own process, into its own process, its own counting process. Then we are going to collect all those people who voted for Donald Trump into its own counting process. And what is the theorem? The theorem is that those people who voted for Donald Trump, they form a Poisson counting process with some rate. And those people who voted for Joe Biden, they also form a Poisson counting process with some rate. I just told you the theorem. Okay? So the story, I already told the story here. So we are going to split a Poisson process into two counting processes, N1T and N2T. Whenever there's an arrival, that means whenever someone walks into the voting booth, is assigned, he or she is assigned as type 1 and type 2 with probability P and 1 minus P respectively. Okay, Europe. The resulting processes, I already told you the story. N1T and N2T are Poisson processes with rates lambda P and lambda PT. Maybe we can say with rates lambda P and 1 minus P lambda respectively. This is the first statement. Moreover, N1 T is independent of N2T. Okay, so there are two statements to prove here, and we'll prove them in one sweep in the next 5 minutes. So, the people who voted, the process concerning the people who voted for Donald Trump is independent of the process of the people who voted for Joe Biden. Okay, as long as if a person comes into the voting booth, he or she tosses a coin, fair coin, not fair coin, the coin P1 minus P is not fair. Okay, but independent of the next person. That means I vote whoever I vote for, and whoever I vote for, independent. All right. Otherwise, this doesn't work. All right. Okay. So good. So we are going to prove this, and this is not very difficult. So let's consider the event NT equals to M plus K. Consider this event where M and K are non-negative integers. Okay. Consider this event. So what we're going to do? We're going to say that actually NT, the total number of people who walk into a voting booth is M plus K. But N people voted for Joe Biden and K people voted for Donald Trump. How do we formulate this? All right. So we will consider the probability that N1 of T is equal to M, N2 of T is equal to K, condition on NT equals to M plus K. Okay, so total number of people who walked into the voting booth up to time T is M plus K. Now, we consider the event that M people voted for Joe Biden and the remaining people voted for Donald Trump. So what is this probability? Okay, there are total number of M plus K total number of events. And M succeeded, say Joe Biden succeeded, all right? And not Joe Biden is failed. So we have M plus K choose M, P to the power M, 1 minus P to the power K, right? That's it, right? So, but now let's apply Bayes' rule. We have that this probability here can be rewritten using Bayes' rule to be probability N1 of T equals to M, comma, N2 of T equals to K, comma, N of T equals to M plus K, divide by probability N T equals to M plus K. Right? This is everything this is Bayes' rule. But this can be simplified. How can we simplify this? The top is too complicated. If we know that N1 is M and N2 is K, we already know that the sum is M plus K. So this can be removed safely. Okay? But we already know that the bottom is Poisson, all right? And this conditional probability is binomial. So what we have is the following, that the numerator is equal to probability nt equals to m plus k multiplied by this guy here. This is the conditional. Okay. So we can rewrite this in this way. Let me make this look nicer. This thing's not cooperating now. Okay, so we have this. This is just rearrangement, right? But we can rewrite this as this is Poisson. So e to the minus lambda t, e to the minus lambda t, let me not put this bracket here. Lambda t to the m plus k over m plus k factorial. Now we can then expand all this. So let's call this the red part. We have m plus k factorial over m factorial k factorial p to the power m1 minus p to the k. The red part is written in the red. Almost done. All right, you see that if math is done correctly, it is beautiful. You can cancel. If math is done correctly, if it's done wrongly, sorry. All right. So now we can actually do a little bit more. We can rewrite this as e to the minus lambda t. We have lambda p t to the power m. You are absorbing this one here, absorbs this one, and the m part of this one. And then what we have here is lambda 1 minus pt to the power k. This absorbs this part here. Oh, this is very ugly, this color. This absorbs this blue part here. Okay, this absorbs the blue part here, as well as the exponent k here. Right? And now we are going to do this. We are not done yet at the bottom. We have m factorial, k factorial. So we can rewrite this as lambda pt to the power k. We are going to split this exponential into lambda pt over. It's better to put this m over m factorial multiplied by lambda 1 minus pt to the power k e to the minus lambda 1 minus pt over k factorial. And you notice what? Okay, that this is nothing but, okay, let me copy this down so it's all on the same page. What we have shown here is that this is equal to that. So this part here can be interpreted as this part here. So this is a Poisson random variable. It's a Poisson distribution, right? And what we have is that this part here is another Poisson distribution. This part here is another Poisson distribution. So what we have shown here is that, up to this point is that n1 of t is distributed as Poisson lambda pt, n2 of t is distributed as Poisson lambda 1 minus pt, and n1 of t is independent of n2 of t. But we are not done. We have only shown that these two random variables are independent. We have not shown that the process is independent. The two processes are independent. We have done the majority of the job. That is to show that these two random variables have the desired Poisson distributions. Okay, but we have not shown the whole thing, and that is to show that we also need to show that n1 of t, the entire process, is independent of the entire process here. But this can be formally done, though it's a bit painful. by using the SIP and IIP of the individual N1 and N2 processes. Okay, so this we will not do. But all you have to remember here is how we got this. And furthermore, what is the theorem? This is the main theorem here, that if I split a Poisson process into two, like people going into the voting booth and voting for Joe Biden and Donald Trump, then we have that the process of people voting for Joe Biden is a Poisson process. And similarly for people voting for Donald Trump. And these two processes are independent. Okay, I have not done the full proof, but I've done partial. And that's good enough for us. So I know that today we covered a lot, but we covered the majority of Poisson processes already. Next time, we will do some problems, practice problems, and we will complete our discussion, and we will talk about conditional arrival densities and order statistics. Order statistics is very cool, right? So that is perhaps the most interesting part of Poisson processes. And we will have more time next time to work out some examples that I will take from the book. So that will serve as some tutorial. Okay. So thank you very much for your kind attention, people here and people in the Zoom. And I will post problem set 5 very soon, together with the solutions for problem set 4. And remember, for the people here and people at home, we will have a lecture next week, same time, different place. Okay. Hopefully that system will also work well. Okay, I will send a reminder. Okay, thank you very much, and good night, and have a happy weekend. Bye bye.